We've now got a little bit of a lull, so it is time to start. It is my pleasure to introduce Dr. Kevin Hand, who is visiting this week with us. And I thank you for agreeing to join our chili cook-off last night and talk to some of you out there. I do have notes, and I think I can cover your background adequately for this presentation. Kevin is a New Englander, grew up in Vermont and went to school in the other state next to it, New Hampshire at Dartmouth. Double major in I want to say the physics of psychology, but a double major in physics and I assume it's psychology according to your CV. He went to Stanford and was on the professional student track because he got a BS in mechanical engineering before getting a PhD in environmental or geological and environmental sciences at Stanford, which has served him well. He's learned how to make instruments that can fly out into space and measure things and tell us about where we might have come from and how we might have gotten here. Kevin is interested in the origins and evolution of life, and particularly, are we alone here in this solar system or our universe? He's been Deputy Director at JPL for Solar System Exploration, project scientist for NASA's Europa lander mission concept, then on Sherlock spectrometer on the Mars Perseverance rover, Europa Clipper mission, and co-I on the Titan Dragonfly mission. He also works on Earth. He's been to the dry valleys of Antarctica, worked in Kilimanjaro. This past fall, he was up in the Arctic sampling. And did you dive with James Cameron, or were we just on that expedition to the Marianas Trench?
Was out there with robotic vehicles, okay, but then dove on the Russian submersibles years ago, which...
I could go on, but I would much rather hear him speak. And Kevin is talking today, I think I have this right, Alien Oceans, the Search for Life in the Depths of Space. Welcome, Kevin.
Thanks, Jim. And thank you all for coming and for the invitation to come and share some of my research with you all. The title that you just read is actually the title of my book, which I'll get it. But the title of the talk, I'll be focusing on ice shells as a lens into the chemistry and habitability of ocean worlds. For the most part, the ice shells are our limit into understanding these far and distant oceans. But before I get into those ocean worlds, I just kind of want to provide a little bit of a roadmap for my research and what I'm going to talk about today. As Jim mentioned, my work covers a wide variety of avenues, from lab work to field work, missions to expeditions, and this is kind of what those lines of research look like. I've got theory and modeling, lab experiments, field work, and missions. I'm not going to go through each of these bubbles in the interest of time. Today, I'm going to concentrate and bounce through the ones that are shaded gray. And a lot of this work has been made possible by just an incredible cadre of students throughout the years who've worked in my lab, worked in the field, worked on models, and worked on missions. So the work that I'm presenting today is not just my work, it's the work of our team, of our lab, and many of these students have gone on to great jobs at NASA, in industry, in academia, and it's a great group. With that, we have been exploring our solar system robotically now for about 62 years. The Mariner 2 flyby of Venus was in 1962. And since that time, NASA and the other space agencies around the world have constructed and launched a host of spacecraft that have gone out to the various worlds in our solar system. This beautiful chart shows a line for each of the robotic spacecraft that have been launched to explore our solar system. And you see many lines that go out to the moon, into Mars, into Venus. a few off to the sun. But there are very few spacecraft, very few lines that have gone out beyond the asteroid belt. Those lines represent spacecraft with names like Pioneer and Voyager, more recently Galileo and Cassini and New Horizons and Juno. And by merit of these few spacecraft, we have made, see, it looks like there's a student trying to get in back there. Maybe the door's locked. By merit of these few spacecraft, we have made what is arguably, I would say, one of the most exciting and compelling discoveries in the exploration of our solar system. And that is that we now have good reason to predict that oceans exist beyond Earth. Liquid water, salty oceans likely exist beneath the icy shells of many moons of our outer solar system. And shown here is a portrait of these ocean worlds of our solar system. At the center, of course, is the Earth with the ocean that we know and love and need to protect. And around the Earth, I've placed Europa, Ganymede, and Callisto, 3 moons of Jupiter. I've got Titan and Enceladus, 2 moons of Saturn. And I've even included Triton, a moon of Neptune here. These are worlds that are covered in ice, but beneath their ice may well be liquid water oceans today. And the discovery of these oceans is really significant for 2 primary reasons, I would say. One is that we can now begin to engage in a field of comparative oceanography. Think about it. With the first flyby of Venus, we began as planetary scientists to do comparative atmospheric chemistry. We could understand Venus's atmosphere, Mars's atmosphere, Earth's atmosphere, and kind of learn from the different planets about their atmospheres, but also then reflect back home on what's happening with our atmosphere. With Venus, the greenhouse effect and global warming is one of the most salient examples. With the discovery of these oceans, we now have the opportunity, with the missions that are to come, to compare our own ocean to these oceans beyond Earth and to better understand the fundamentals of the physics, chemistry, geology, and ultimately the habitability of these worlds. Now, the second major thing is, of course, the fact that if we've learned anything from life on Earth, it's that where you find the liquid water, you almost always find life. Whether it's life in extreme environments like the Rift Valley or Antarctica or hydrothermal vents, from life in extreme environments to life of extreme lifestyles, all life on Earth depends on liquid water. And I like to show this montage for another reason, and that is that for all of the morphologic diversity of life on Earth, from the most extreme of microbe to the most extreme of rock star, even though we're physically quite different, we're all connected, of course, by the same genetic tree of life. We are all somewhere on this map. And just to orient you, Mick and Keith, along with us, we're down here. So when it comes to ocean worlds, part of what is so exciting is the prospect of seeing whether or not these worlds where oceans exist today could have given rise to a second independent origin of life, a chance for contingent and convergent biochemistry to maybe have unfolded. Is DNA, RNA, and ATP, is that the only game in town? Or is there a different way to get the business of life done? And that's an important contrast with our search for life on Mars. I love Mars. I do a lot of work on Mars. This is an image of the Perseverance rover after having collected 2 cores that I helped coordinate on the Perseverance team. And we will eventually get these cores back, and we'll be able to look into deep time on Mars to understand the evolution and history of that planet and to look for any biosignatures. But if Earth is any guide, we know that the large molecules of life, like DNA and even proteins, they don't last long. If you look at the oldest rocks on Earth, you're not going to find DNA or proteins. At best, you'll see some isotopic evidence for life. And depending on what kind of processes have affected those rocks, maybe you can get some organics out of them. So incredibly important, but I really want to see whether or not there is an independent origin, and if there is life that is extant, living today, what makes it tick. And so that is what motivates my interest in worlds like this, Europa. Europa, covered in ice, all of these fractures created from the tidal tug and pull as Europa orbits Jupiter, shown here. Europa is about the size of our moon, shown to scale relative to the Earth, and all three of which are shown to scale relative to Jupiter. Jupiter is 318 times as massive as the Earth. And we all appreciate the tides on Earth. Well, if you could stand on Europa, some predictions indicate that with the orbit of Europa being 3.55 days, you would rise and fall by about 100 feet due to the tidal stretching of Europa's ice shell. And it's that tidal dissipation that gives rise to the internal heating, which then sustains the ocean beneath the ice. Now, if I had more time, I would kind of go through discovering an ocean in what I like to call 3 easy pieces. I'm not going to do that today. I'm going to make a shameless plug. If you want to learn more about that, read my book. I go into a lot of the physics and really cool history of how we think we know Europa's ocean exists, and it spans from the history of spectroscopy to gravity flybys to metal detectors at airports. But with these 3 easy pieces, we have constructed a model for Europa, an understanding of Europa, that looks like this, where it's got an iron-rich core, maybe some sulfur mixed in there, a silicate mantle, and above that mantle is an ocean that's perhaps 100 kilometers in depth. And then overlying that ocean is this ice shell that's perhaps a few to as many as perhaps 30 kilometers in thickness. This is one of the great debates in the planetary Europa community, is how thick is the ice shell. But I show this in part just to provide that connection between the ocean and the surface. The colors that you see there are meant to represent buoyant diapirs of ice, perhaps upwelling and bringing oceanic material to the surface. And this is where we get into this topic of ice shells as lenses into the subsurface. And I like to break that up into 2 primary realms of importance that I pursue with my work. First is understanding the surface composition. So if we understand the surface composition of the ice shell, we are learning something about exogenous stuff that's coming into Europa, meteoritic infall, etc. And then there's also some endogenous influences, stuff coming up from the ocean below. And to the extent that we can partition out the exogenous from the endogenous, we have a proxy for ocean composition. And once we've got a proxy for ocean composition, then we can really better understand the geochemistry of that ocean and potentially the habitability. And then another component of my research that focuses on ice shells is the surface morphology. What does ice and what do these surfaces look like at the centimeter to meter scale, which is below the resolution of our Galileo spacecraft imagery, and will even be below the highest resolution imagery that we'll get from the Europa Clipper, which I'll talk about later. That morphology is important because it affects the photons that are reflecting off and through the surface, from which we then get our compositional interpretation and our radar measurements, our thermal measurements, and so on and so forth. And these 2 primary components on the left, I then convolve with the keystones for habitability, which are, of course, the need for liquid water, the need for the elements that build life, and some form of energy to power life. Now, Europa in particular has a curious component to the exogenous story and what modifies its fingerprint. This is I drew this diagram over 20 years ago on an acetate. I realize that's out of date, when you used to have an overhead projector with acetate films, but it still gets the job done. Shown there is Jupiter with the magnetic field. Europa at the center gets bombarded by electrons and ions that are entrained in Jupiter's magnetic field. And those energetic particles then do radiolytic processing of Europa's surface. And so that radiolytic processing provides an added component that can confuse the differentiation between the exogenous materials and the endogenous materials. And it also will end up being, as you'll hear throughout this talk, a very important component in helping us understand some of that ocean chemistry and potentially helping solve some of the problems of energy as a keystone for life. So I'll start with elements, getting into what do we think we know about that ocean chemistry and how does that play into its habitability. This is what Europa looks like somewhat up close. We don't really have much in the way of high resolution images from the Galileo spacecraft. And the first thing that will capture your eye, well, I guess for geologists, the first thing that will capture your eye is the incredible tectonics. The tidal cracking of this ice shell leads to all sorts of strike-slip faults and extensional faults and maybe even some subduction. We just don't know. But beyond the fractures, I want to draw your attention to the different colors. And a key question that came out of the Galileo mission is, are these colors on Europa's surface telling us something about the composition of the ocean? And it was a pretty heated debate because of the following. So the bold line up top there that you see labeled NIMS, that stands for the Near Infrared Mapping Spectrometer, the spectrometer on the Galileo spacecraft. And as you can see, that spectrometer does not have very high spectroscopic resolution. It was built in the late 70s. It was slated to launch in 86. The Galileo spacecraft didn't launch until 89. And so by the time it got out to the Jovian system in the late 90s, this spectrometer, even though it was state of the art in the 70s, was way out of date. So without much spectroscopic resolution, a debate ensued as to whether or not these absorption features, specifically in kind of the 1.5 and 2 micron region that is indicative of water, then some of the little dips and nuances within there, some would say are indicative of frozen brine, which is exciting because that would say, hey, this is Europa salts on the surface. And so this coloration that we're seeing on Europa is due to material coming from the ocean below. But then a perhaps more parsimonious hypothesis was, and less extraordinary, was that really what we're seeing is sulfuric acid hydrate. You might say, sulfuric acid hydrate, that doesn't sound like an easier hypothesis. How the heck would you get sulfuric acid on the surface of Europa? Well, the culprit is Io. Io is Jupiter's innermost large moon. It's the most volcanically active body in the solar system. It's spewing out sulfur into Jupiter's environment, and that gets entrained in the magnetic field. And so part of the radiation bombardment that occurs on Europa is from sulfur ions. And those sulfur ions then get radiolytically processed to H2SO4, which then has some water bound to it, creating sulfuric acid on the surface. And so that debate ensued, and the spectroscopic resolution of NIMS was insufficient to really resolve that. And that's where I sort of come into the picture, trying to figure out what this yellow, reddish, brown material is on Europa's surface, and does it tell us anything about the ocean? And you can see some of these hypotheses: exogenous, sulfuric acid hydrate; endogenous, magnesium sulfate hydrate. With my colleague Mike Brown, we also looked at kind of a hybrid there. But then I really focused in on something else altogether, and that brings us to my lab, the Ocean Worlds lab at JPL, where again, a lot of this work is done in partnership with a great group of students and postdocs. Here's what part of my lab looks like. And I endearingly refer to these as Europa in a can, or Enceladus in a can, or Ganymede in a can, depending on which world I've got funding for. And so these ultra-high vacuum chambers, since I can't wake up in the morning and go to Europa, I pump down to Europa temperatures and pressures, pump down and cool down. And then I can grow an ice with this manifold here, or I can put some material directly on the cold finger. This is what it looks like when the lid is off of the chamber. And that gold mirror at the center is where I grow or deposit the sample, and then turn on the electron gun, or with the other chamber, I've got an ion gun. And when these experiments are running, that little 1 centimeter spot in the center, that's as Europa-like as you can get on Earth. And coupled to the chamber, I've got FTIR and RGAs and various instruments that allow me to, in real time, analyze the chemistry of what's happening. So for this particular talk, I want to focus on some experiments that I did with sodium chloride. You might say as geologists, well, you showed magnesium sulfate. In our own ocean, magnesium sulfate is drawn down quite rapidly. The only reason we've got magnesium really in our ocean is because of continental weathering. Why the heck would anybody focus on magnesium sulfate? And I too asked that question. And you all know that the residence time of various ions in our ocean really selects for sodium and chlorine. Having long residence times, they don't get drawn out as water cycles through the oceanic crust. And so our ocean is dominated by NaCl in part because of that residence time component. So why the heck, if Europa's got a long-lived ocean, wouldn't it be dominated by sodium chloride? To me, the answer was it's got to be if it's been there for billions of years. Operationally, and from an implementation standpoint, the reason people really hadn't investigated it much is because sodium chloride is spectroscopically flat. Alkali halides, for those of you that do infrared spectroscopy, you often will use like KBR beads or various alkali halide components just to improve the scattering without increasing the absorption. So alkali halides have been mostly ignored because, well, we can't detect them spectroscopically anyway, so what's the point? However, alkali halides have this beautiful characteristic where they love to trap electrons. And so when I did this irradiation, after the irradiation, sodium chloride looked like this. These are some of the grains. I did it with sodium chloride grains. I did it with evaporites. Here's a video from inside the chamber. That's the electron gun rastering over it. After I pulled it out, the sodium chloride turned this yellow color. All the while, as I'm doing these experiments, I've got a picture of Europa above the chamber showing this yellow, reddish brown. And with each experiment, my jaw is just dropping because these sodium chlorides look just like the surface of Europa in different regions. Now, what's actually happening to the alkali halides? It's some really cool quantum mechanics where you in an idealized case, take that perfect crystal, you do a double ionization, and eventually you've got an anion hole that an electron can fill. And then that electron to quantum physicists is really exciting. A lot of the early literature on this actually goes back to the Manhattan Project and early days of quantum mechanics because this trapped electron in alkali halides is a good harmonic oscillator. Now, cool physics, that's not what I was there for, but when I went down that rabbit hole, it was a lot of fun. What I was there to better understand is, well, now that I've got this visually interesting irradiated sodium chloride, can I spectroscopically pin it down? And so those trapped electrons make that yellowish, brownish color by some very specific absorptions. In the case of sodium chloride, it's what's called an F center at 460 nanometers and an M center, which is 2 F centers, at about 720 nanometers. I went back to the Galileo data. We didn't collect spectra in the visible part of the spectrum, but we did have some filters on the solid state imager. You can see those filters in the color bars there. Not a direct match by any means, but that was at least the best we could do at that time. Following on that, teaming up with my colleague Mike Brown and employing a student, Samantha Trumbo at Caltech, we went after some Hubble time and we collected data with Hubble of Europa. And when I first saw these spectra with, so in black up there, the sort of higher noise spectrum there, that's Hubble data. In red is my lab data, and that roughly 450 nanometer absorption that you're seeing, that is the epicenter of sodium chloride. And so sure enough, we were able to map that 450 nanometer absorption feature, which is highly diagnostic and very specific to irradiated sodium chloride, to the leading hemisphere, most yellowish patch of Europa. So this was just a beautiful hypothesis, experiment, prediction, get the data from Hubble, and then really nail down that assignment with the spectra from Hubble. And I do believe that this is the best indication that we have at this point of water rock chemistry in Europa's ocean, an indication that this ocean is long-lived, that it is cycling with the sea floor. And then subsequent to that work, we also got some James Webb Space Telescope time. And we found in direct spatial association with the sodium chloride, carbon dioxide. Why is that interesting? Well, it implicates, the salts clearly implicate that we've got endogenous material coming up from the ocean below. And then the observation, the measurement spectroscopically of carbon dioxide in direct association with those salts is an indicator that the carbon dioxide is also coming up from the ocean below. Now, there may be some radiation processing, maybe there's some bicarbonate, there's some carbonic acid that's then getting radiolytically processed to CO2. But I do believe that this is an indication of endogenous carbon coming up from Europa's ocean. Along with looking at these alkali halide color centers as an indication of endogenous chemistry, just a couple of highlights. One of my postdocs looked into whether or not we could use the band depth as a clock for how old the surface of Europa is. Turns out the short answer to that question is yes, as long as the surface ice is very, very young. It doesn't, the band depth gets saturated once you get beyond thousands of years. We also took this concept to Ceres and Mars, looking for irradiated alkali halides on those worlds, because even though they don't get the same level of irradiation that Europa gets, galactic cosmic rays, solar wind, etc., does impart quite a bit of irradiation on these worlds. And sure enough, we were able to implicate irradiated NCL on these worlds. This was work led by my former postdoc, Michael Bramble. So that's the element side. The irradiation, the discovery of sodium chloride, I think provides the best indication of water rock leaching, water rock interactions that make for a geochemically rich ocean, at least beneath the ice shell of Europa. We have not seen these alkali halide color centers on Enceladus yet. That's ongoing work. So let me switch to the keystone of energy. On Earth, of course, we've got an oxidant-rich atmosphere made in large part possible by photosynthesis. And deep in the depths of our ocean, we've got these engines of reductant chemistry spewing out hydrogen, methane, sulfides, etc. But on an ice-covered ocean world, even if it is geologically active and, say, has hydrothermal vents, might the habitability of that world be oxidant limited? You may well have a tremendous source of reductants coming from the seafloor, but if there's no oxidants, it might be game over. And just to kind of put that in a little bit of context, when we think about life, life alleviates chemical disequilibrium in the environment. Even though we like to think that we are somewhat fancy and special, we as humans and organisms are not that much different from a battery that you put in a flashlight. In the geologic environment, if you just went to a convenience store and bought some batteries and left them out on your table, eventually the battery would lose its charge over many years. But if you stick it in a flashlight, turn that flashlight on, now you drain the energy in that battery much quicker, but it's because you're getting work done, biology connects the positive and negative terminals in the geochemical environment to get the work of life done. And whether it's oxygen and reduced materials in wood, or us and our carbohydrates and other things we eat, or microbes that combine oxidants and reductants in many different forms, without connecting the circuit, without completing the circuit geochemically, life cannot survive. And so even if Europa does have hydrothermal chemistry, it could be game over without a source of oxidants. Well, here's where the radiation environment might solve the problem. This is kind of a diagram showing all the different energy sources. And the charged particle of radiation on Europa amounts to about 125 milliwatts per square meter. That's quite a bit of energy, and that radiolytic chemistry, once it starts processing and chemically modifying the H2O, the water on the surface, some of that H2O gets split apart into H plus OH. Some of the OH combines with other OH, forming H2O2. That's hydrogen peroxide. Some of that then gets irradiated to H2 plus O2. And before you know it, you have got an ice shell that is rich in hydrogen peroxide and condensed phase oxygen. And so on Europa, the Galileo spacecraft measured hydrogen peroxide near 3.5 microns. I followed that up using the Keck telescopes. We now have a pretty thorough map of Europa's surface and the abundance of peroxide and oxygen on Europa's surface. In brief, if you took pharmacy grade 3% solution of peroxide and diluted it with about 3 gallons of water, you would have the roughly 0.13% by number abundance that we see on Europa's surface. And so on Europa's surface, we have got the source of radiolytically produced oxidants: hydrogen peroxide, oxygen. We've also got sulfates and a number of, maybe even ozone. And so then the question becomes, well, how oxidized might Europa's ocean actually be? And this is a somewhat of a complicated chart. Moles delivered to the ocean per year, and then delivery period. This is how often does the ice shell overturn and deliver those surface oxidants to the ocean below. We don't really know where Europa's ice shell falls in the x-axis here, because we don't know that much about the geological processing on Europa. That said, just doing crater counts, we can constrain the surface age to somewhere in the range of 20 to 80 million years. And so if you make a few assumptions about oceanic delivery from ice on the surface, you can actually get Europa's ocean to be oxygen rich at levels that exceed the O2 minima zones found here in Earth's ocean. That's pretty extraordinary. Coupled with that, there's a ton of sulfate on Europa's surface, and so sulfate is going to be delivered at roughly an order of magnitude greater abundance than oxygen or peroxide. And so the radiation of Europa's surface, even though it can prove challenging from a modification of the surface standpoint, and incredibly challenging from a spacecraft radiation hardening standpoint, it may be that the radiolytic processing solves the oxidant problem for the habitability of Europa's ocean. And so returning to these keystones, salts, I think, are the best indication that we can check the box on the elements for life. And then surface oxidants produced radiolytically, I think, checks the box for completing the energy circuit that's needed for life. All right, I want to pivot to morphology now. And again, this is morphology at the centimeter to meter scale. At the large scale, as you recall from that image I showed earlier, Europa's surface is dominated by tectonics and fracturing that is largely due to the creaking and cracking of the ice shell as Europa goes around Jupiter. At the centimeter to meter scale, though, Europa has no atmosphere. There's no aeolian erosion, there's no fluvial erosion. The erosion that occurs on Europa's surface without an atmosphere, just dealing with the harsh vacuum of space, the erosion is primarily driven by sublimation. And so the reason that understanding this morphology is important is because with Europa Clipper, with our remote sensing, with our ice penetrating radar, that morphology is going to be sort of the first layer that we encounter as we try and do our remote sensing and ultimately sampling with a lander. Now, to understand some of this morphology, I want to bring you quickly out to the northern ice field of Kilimanjaro. I did some work up here years ago, and the reason that they're relevant to this question is that the thin atmosphere at that altitude and the location near the equator leads to a lot of interesting sublimation-driven morphologies on these ice fields. In particular, the formation of these spikes known as penitentes. These spikes form in part from a combination of sublimation being a kind of dominant way in which you can lose water molecules, and then a feedback mechanism where self-illumination in the valleys leads to greater heating in the valleys and faster sublimation and erosion within the valleys. And visually, you can almost see that in this image where the valleys look brighter than the peaks, and so intuitively it kind of makes sense that those would be a bit hotter. And so there's sort of a debate about, well, you know, there's no way that you can land on Europa or Enceladus or these other worlds because they're going to have these huge spikes on them. And so that debate has gone back and forth a little bit. But my argument, and I think this is based on pretty solid physics, the physics of penitente formation just does not apply to a world without an atmosphere. This nice paper by Claudin et al. Went through the formulation of the dispersion relation for how these morphologies arise in an environment where you've got some degree of sublimation, but still you're in the fluid regime. When you migrate to having essentially no atmosphere, what happens when you do the math is that your penitente wavelength essentially goes to zero. In other words, you get runaway sublimation and you flatten out any spikes that you once had. So on the theory side, the physics of penitente formation does not apply on worlds like Europa. On the experimental side, I wanted to actually test this. Let's see what happens, because even if the physics of penitente is not relevant to Europa, still there might be something curious happening at the centimeter scale, and that's where experiments are great. We can just kind of do hypothesis and discovery-driven science. So we built this large chamber. In my lab that we endearingly call the Arc of Europa. Here it is during a freeze phase. This is just a beautiful time lapse showing the ice forming inside the chamber. It's about 1.2 meters in length and about 0.4 meters in width on the inside. And we can run these experiments where we're at Europa temperatures and pressures, and then we can raster this LED bar over the surface. This LED bar, we selected LEDs to replicate solar irradiance. We can modulate that irradiance to 5.2 AU out, which is the Jovian distance from the sun. And we can then, over time, just see what happens. Now, this experiment took us about 7 months. And I would run it longer, but actually the building at JPL where my lab is located, it is unstable on timescales of about 7 months. In other words, inevitably we have a power outage or something goes wrong. And so we're always kind of monitoring with the facilities folks of, something going to go wrong in the building today. And so Gradually, we increase the temperature just to kind of accelerate the pace at which we can see changes. This video is quite long. I'm just kind of skip to sort of the final image. And here's what we saw. Instead of seeing spikes or penitentes, we actually saw this botryoidal type structure. It almost looks like an ice version of malachite. And it turns out that these botryoidal structures did not form due to the solar irradiance. Instead, they actually formed in regions of the chamber that just happen to be slightly colder. So this is cold trapping occurring. And I think in the colder regions and maybe the shadowed regions of Europa, this is the kind of morphology we might be seeing. This may in fact be the kinds of morphology of ice on the moon, where over millions to billions of years, you've got cold trapping of water molecules. And so that was one of the initial experiments we did. Then we also seeded the chamber with a corrugated snow sample to see whether or not there would be a positive feedback loop and whether or not these penitente forms might grow if we just seeded the chamber with a preformed setup. And here again, you can see the valleys look brighter, and so you might say, well, you're going to have enhanced sublimation in the valleys, so you might expect the spikes to increase. But given that there's no atmosphere, there's no kind of molecular bouncing with each other to help reinforce the heating, the mean free path of a water molecule here goes off for, on Europa, tens, hundreds, maybe even thousands of kilometers, depending on the exact temperature. And so what we saw over time is that the edge gradually eroded and that corrugated cake went to flat. And so with sublimation-driven erosion on a world like Europa, if you focus on the peaks here, you'll see those gradually decrease, whereas the valleys actually stay the same. And that kind of makes sense. In a vacuum environment, the 1/2 kT of a water molecule wanting to pop off, it's going to be more energetically favorable for it to pop off at the peak. And so with this work, we also had some coupled models led by a number of students where we could then validate what we were seeing with the experiments in the arc chamber, and then computationally create all sorts of different morphologies, starting with the triangle, going to convex and concave, sinusoidal, different size scales, different aspect ratios. And in all cases, we saw that the migration of the surface is towards flat. Okay, so that's a bit on kind of the ice as windows, the chemistry, the morphology. Now I want to close with a bit about what's next and go through some of the missions and some of the field work. Well, within the next decade, we will have 2 spacecraft out in the Jovian system, Europa Clipper and the Jupiter Icy Moons Explorer, which was built and launched by the European Space Agency. Europa will orbit Jupiter and Europa Clipper will orbit Jupiter and fly by Europa. JUICE will make some flybys of the moons and then go into orbit around Ganymede. I was fortunate enough to be at the launch of Clipper this past October. This really was quite an emotional event. I first got involved with this mission before it was even named Europa Clipper. I was on what were called science definition teams for variations on this mission starting in 2006. And so here we are almost 20 years later, and it finally launched. I am a co-investigator on one of the mass spectrometers, the SUDA dust analyzer. This is a mass spectrometer that will collect material sputtered off of Europa's surface and material that's erupted from any plumes that we find on Europa. And so Europa is, we just did a flyby of Mars, a gravity assist with Mars this past weekend. That was successful. And then in 2030, we'll go into orbit around Jupiter, we'll pinball around, do some gravity maneuvers with Ganymede. And then in 2031, we'll start doing these pedals that take about 2 weeks, where we orbit Jupiter, and with each orbit, we fly close past Europa. And all of those instruments that you saw will be operating at the same time, nadir pointing, ram direction pointing, just collecting incredible data about Europa's surface with the overarching goal of assessing the habitability of Europa through imagery, spectroscopy, ice penetrating radar, and gravity measurements. In just a few years, we'll get this spacecraft, this mission to the launch pad, the Dragonfly mission. I'm a co-I on this. This is a New Frontiers class mission. It's built and operated by the Applied Physics Laboratory down at Johns Hopkins. With any luck, we'll launch in 2028, I think, at this point. And I think we're still on schedule to land in 2035. This mission will land outside of one of the large craters of Titan, and then we'll examine the chemistry of the surface materials on Titan, and then we'll hover and look for another landing site and eventually land at a different spot, and we'll continue to kind of hopscotch towards Selk crater on Titan, and eventually maybe even get into that crater. We'll see how long the mission lasts. This is an incredibly ambitious and exciting mission. To fly a drone essentially on Saturn's moon Titan is just really science fiction coming to life. Now, as excited as I am about these missions and to get the data back, and these are great opportunities for students to work on that data, to work on getting missions like this to Launchpad, et cetera, a lot of great opportunities. One of the things that I find really interesting and important about Ocean World's exploration is the connection to advancing exploration and measurements here on Earth. And by analogy, just think about Mars exploration. Long before we have sent any rover to Mars, the engineers and science teams have taken those rovers out to the Mojave Desert or the Atacama or some Mars-like place on Earth to literally kick the tires and see how everything works with the prototypes for that mission. The long-term vision for Ocean Worlds is not just flying by, not just landing, but also getting through the ice, down into the ocean, and ultimately to the seafloor. Now, this is a century-level ambition and timescale, but still, that is where I hope we are decades to a century from now, exploring the hydrothermal vents within Europa's ocean, right up square with a European octopus, who knows. But to get to there, we need to really test out our tools and technology here on Earth, and there's a great win-win of bringing some of the space technology down to Earth and deploying it and developing it in Earth's ocean and cryosphere. And I've had the opportunity to work on these 3 vehicles. I'm just going to highlight this one that our team invented. It's called the Buoyant Rover for Under Ice Exploration. The penguin is shown for scale here. One of my particular regions of interest scientifically is the ice-water interface. Life loves interfaces, and a poorly understood interface here on Earth is the ice-water interface from the standpoint of chemical dynamics and habitability. So this rover came about because I was thinking with my team, we had this little ROV, but every time you bring an ROV up to the ice-water interface, the thrusters mess up the interface and destroy exactly what you're trying to study. And it's also power hungry. Where with a rover, you can kind of gently crawl along the ice, and then when you stop, you're not spending any power station keeping. You can just shut down the robot and focus on power needed for the instruments. So we said, while we can build things like this at JPL, let's imagine something that is buoyant, that thinks the up is down, and that's where the Buoyant Rover came about. This is some video from, we did some work down with the Antarctic Australian Division back in 2019. It was frickin' frack, just excited to see what we're doing. The penguins are very friendly. And this is what the rover looks like. We had it on tether just because this was a new environment. We can operate on tether or off tether. And you can see it's just gently going across that surface. And then we can stop and make measurements. We've got instruments on the tail, cameras in the main body there. This is what the underside of that sea ice looks like. These bubbles are all oxygen or dominated by oxygen from just saturation from all the photosynthesis at that time of year. Really cool dynamics. Our goal is to leave this out under the ice down there on some future with some future collaborations. But recently, I got about a $3 million Peace Star award to continue some work that our team had been doing up in Alaska. And this is particularly relevant to our changing planet, to climate change. The permafrost up there is dotted with some 13,000 permafrost lakes, some of which are bubbling out methane. And we know it's methane and ethane because we can chop into these bubbles and light them on fire. Hopefully there's no safety officers in the audience today. And so with the buoyant rover, we can go around and we can monitor these seeps. We can look at the ice-water interface. Those are some bubbles that are trapped in the ice. One of the questions that we're addressing in this grant is, are there psychrophiles living on the inside of these bubbles, metabolizing that methane? Are these seeps changing through time? To what extent are these seeps shutting off during the dark winter? How much methane is coming out? Does this flux change? That all factors into understanding our greenhouse gas inventory. Methane, of course, is a much stronger greenhouse gas. There are a lot of open questions about what exactly is happening in these permafrost regions in Alaska, Siberia, et cetera. And so a lot of the work that's been done, as great as it is kind of these points in time when humans can get out there to make these measurements. Next winter, we're going to leave the buoyant rover out and then joystick it to make measurements in a time period when no human has been out there to observe these methane seeps in the lake. And we'll be able to get a seasonal flux measurement to understand whether or not these are shutting down, whether or not they're increasing, where does that methane go. And so that's an exciting project that links a vehicle that someday I hope makes it to Europa, but in the meantime is advancing our capability to better understand our home planet. That bubble counting work done by a student of mine, had a lot of fun writing that code. And coming back to the ice shells as windows theme, part of what we're looking at in this project is these permafrost lakes are the simplest window for kind of understanding ice as a lens into liquid water regions below. These lakes are 2 meters deep, and they're open to the air in the summer, and then they freeze in the winter. And part of what we're looking at is by sampling the ice, can we do the inverse modeling to understand the chemistry and the biology of the lake itself? And it's incredibly challenging, not surprising. And that's on a 2 meter deep lake. We're looking at the isotopic signature of the methane, and we're also looking at other gases and inorganics and organics trapped in the ice. I'm headed back up there in about a month and a half to get more ice cores to again, look at ice as a lens into a very simplified or what should be a simple environment, but is turning out to be much more complex. And that just is an example of when we do get out to Europa, how challenging it will be to kind of invert our remote sensing and surface measurements to understand that world as a habitable planet. So here's a little bit of the rover view, looking at some of those methane bubbles. And I'll just close with, I've shown a number of images in this presentation. I'll close with one of my all-time favorite images. An image captured, of course, by the hand of Galileo, showing Jupiter at the center there, that wheel-like structure, and these 4 bright dots around Jupiter. Now, when Galileo first started observing Jupiter and noticed these bright spots, he just thought they were stars that he couldn't see with the naked eye. And he named them the Stars of Medici because the Medici family was funding his research. and Galileo was no idiot. I was like, yeah, call them the stars of Medici. Send me a check. But night after night, as you know, he saw that they revolved around Jupiter, which was heretical, and as a result, got him put under house arrest. But with Galileo's observations, he put the final nail in the coffin of the Aristotelian cosmology, the idea that the Earth is at the center and everything revolves around the Earth, and he opened the doorway to the Copernican revolution. And in the decades and centuries that would follow Galileo, we would come to appreciate that the laws of physics work not just here on Earth, but also on worlds and wonders beyond Earth. And then with the advent of spectroscopy, we would come to appreciate that chemistry works beyond Earth. Then with the advent of the space age and our robotic exploration of worlds beyond Earth, we've come to appreciate that the principles of geology work beyond Earth. But when it comes to that fourth fundamental science, physics, chemistry, geology, and biology, when it comes to biology and the phenomenon of life, we have yet to make that leap. We don't yet know whether or not biology works beyond Earth, whether or not there has been a second independent origin, whether or not life on Earth is some sort of biological singularity, or whether or not life arises wherever the conditions are right. And part of what excites me about the time in which we live is that for the first time in human history, we can do these great experiments, launch these missions to go out and explore our solar system and beyond to see whether or not we live in a biological universe. And if we do, we may bring the universe to life. So I'll close there, and hopefully we've got some time for questions. Thank you so much.
The tradition, Kevin, is to allow students who tend to sit on that side of...
I noticed.
Zach.
In your radiated light work, the formation of color centers, I'm sure that's the same phenomenon that makes smoky quartz, but I was curious if any of the colors you observed are reliant on pressure and temperature conditions outside of just the radiation.
Yeah, so far, no, though there, in that paper where we used, where we looked to see if the band depth could be used as a clock, we looked at the annealing timescales. You know, if you warm up to 130 K, so Europa's surface temperature is nominally 100 K. Gets down to 70 K, up to 130 K. Maybe if there's some upwelling, you can get up to 180 K. And so at 180 K, do you anneal those color centers back to kind of a standard bleached white NaCl? And so the short answer is yes. If you get up to higher temperatures, you can anneal, and some of that work is in that paper. Pressure so far, we're operating at vacuum, and they're forming quite well. Mechanistically, I can't imagine what would change other than at higher pressures you might change the conductivity and kind of draw the electron out, but I haven't really investigated that. So it's
David.
Without subduction, how would you get these surface sulfates back to their system?
Yeah, it's a good question and a huge debate. There's really only been one paper published on subduction or subsumption, as they call it, on Europa. And it's been really hard to identify places in Europa's ice shell that have clearly been lost. It's easy to see the extensional features, but not the ones where things are lost. So other than subduction, one of the ways that you can imagine is like a sort of a conveyor belt where if you've got plumes erupting out and then emplacing stuff on the surface, you'll have isostatic compensation, melt at the base, deposition on the surface, melt at the base, deposition on the surface. So that's one way. But you know, once we get Clipper out there, the whole geology of Europa is going to be rewritten.
Paul? And then we'll go back.
So Kevin, I guess we do have evidence, visual evidence of plumes on Enceladus.
Yeah.
Is there any evidence of plumes on Europa?
So it's tenuous. I was on, and I guess technically still on. We've still got the work going, and may have some more observations. But I was on one of the Hubble Space Telescope teams looking for plumes, and there was an initial discovery that was looking at hydrogen and OH excesses. I think they might have seen something, but follow-up observations have not found strong reproducibility in those observations. In our team's observations, we've got some hints of reproducibility and some Six Sigma detections, but I still don't feel like I can point to Europa and say a plume is erupting there. Now, there's some caveats there. Enceladus is 500 kilometers in diameter. Enceladus has the gravity of a comet, basically. As much as I love Enceladus, it's kind of a glorified comet. It might be like this Alka-Seltzer tablet out there orbiting Saturn. And so with Enceladus's plumes, they go out for 500 kilometers. The plumes of Enceladus make the E-ring of Saturn. And so by merit of Enceladus being small and low gravity, the plumes are large and thus visible. Europa, just from a physics standpoint, the plumes should not go much higher than, say, 100 kilometers above Europa's surface. Europa's 3,000 kilometers in diameter, and so when you're trying to look, we were using Jupiter to backlight Europa, looking for water absorptions from plumes, and your pixel width from Hubble and JWST for the most part is of order 100 kilometers out at Europa. And so just because we haven't seen them doesn't mean they're not there. I would be incredibly surprised if we don't find plumes or some sort of geologic activity on Europa with Clipper.
So if you were to send a craft to be a lander, you would want it to be close to a plume?
Well, yes, and there's all sorts of planetary protection issues that unfold when you want to land near a feature that could give you access to the ocean. Because if something goes wrong, heaven forbid, your spacecraft, threads the needle, Luke Skywalker style on the Death Star, going right down into the fracture. Now you've maybe contaminated Europa's ocean with Earth life if you haven't cleaned your spacecraft sufficiently. So scientifically, yes, landing near a plume is great. From an engineering and planetary protection standpoint, there's caveats.
Okay. I guess you can get rid of that one.
Yeah.
Kate, did you? Yeah.
Yeah, with these methane seeps that you were doing some work with, do you think that these same driving mechanisms could be related to why Titan retains a methane atmosphere instead of catalysis, like forming more stable molecules over time?
Yeah, short answer, Kate, is I don't know. But there's a really cool thing up there in the permafrost that's not yet part of our project, but there's actually an impact crater in the Alaskan permafrost up in that region. And I've talked with some of the oil and gas folks about getting access to their cores to kind of look at this thermogenic versus modern biogenic connection, and if there's anything distinct about the methane signal within that impact crater region versus outside. Because of course on Titan, the impact craters may kind of open up pathways for delivery of methane trapped in the interior to the atmosphere. So, I've noodled around with some thoughts along those lines, and part of this project is connecting to the Dragonfly mission and using the Dragonfly mass spectrometer up in the field to kind of kick the tires on that instrument before we bolt it onto the spacecraft.
Those cores are down the street.
What's that?
Those cores are in the Exxon library down the street.
Oh, they are from up in Alaska. Oh, that's good to know. Yeah.
Alan?
Can I just hit the ice shell, especially if they come on Europa, interfering with how we're able to communicate with an underwater weather?
Yeah, absolutely. In kind of my dream of dream missions, We land, we've got a melt probe. The melt probe leaves behind a fiber optic and also deploys some acoustic sondes so that we've got a fiber back up to a spacecraft on the surface. That spacecraft then can radiate uplink and downlink to Earth, and the acoustic sondes can then serve as a backup. But we've had some things funded and some work done in Antarctica that provide a bit of a proof of concept for getting into the subglacial lakes beneath the Antarctic ice sheet, beneath the Greenland ice sheet. And I would say there is a really nice example of a scientific and engineering desirement here on Earth of getting beneath ice sheets on Earth to better understand what's happening, and a bridge to NASA with technologies that are low mass, low power, miniaturized, that could potentially be deployed as we're building that capability for a world like Europa.
How do you anticipate getting below the surface of the ice moons if you're not going to go through the plumes?
Yeah, so it's going to necessitate radioisotope thermoelectric generators landing large masses of material that can provide the power on the surface to then drive either a probe that's got a nose cone that's heated and or that also has drills on it. And so that melt probe would melt the ice, drill through any salts, et cetera, that might impede progress. But similar to what we do on Earth, where you use a hot water drill, you would just have that system embedded in a probe that goes to the ice. And that's part of why this is like decades to a century from now. But hopefully someday we'll do it.
Is there anybody online, Kim?
No, there were no questions.
All right, well, let's thank Kevin again.
Thank you so much.